Can you just confirm that you can hear me again? Can somebody confirm that we can hear
Yes,
you?
yes.
Can hear you.
Okay, yeah. Okay, so so today we are going to cover SAT+SMT preliminaries, and today I'm going to set up the story behind SAT and SMT solvers. And the purpose of this discussion is to make sure you have some background, some understanding of the terminology that is going to be used in the rest of the 3 days. Okay. So in this particular talk, I'm not going to go in depth of many of the arguments I'm going to present. I'm going to just show you, try to give you some intuition. But forgive me if I don't really elaborate in depth, like why that argument holds or not. But we will have discussion. If you really want to ask something, please go ahead and put something on chat. I can then ask the questions. Okay. And there will be question. I will be asking few questions here and there, and I would please sometimes you can answer by chat. Sometimes you should. I would expect you to just discuss with me. Okay. So that will come at the end. Let's see. Okay, so what's the plan? The plan is the first we will go over this satisfiability problem. So I need to turn on my video. Yes, yeah. So first I have to discuss the satisfiability problem, and that's uh, and then I will discuss a couple of ideas like negation normal forms and conjunctive normal form, where that's how the solvers take their input. They don't want to take inputs in arbitrary formulas. They almost any tool you build in your life, you will realize that always you expect your inputs to follow certain patterns and structures, so then you can easily process them and communicate and interoperability between the tools. So that's we will cover this idea. We will pick a problem and try to encode into SAT problem and run a tool and see how that behaves. So that just gives you some sort of a sense that this is not fun and games. Sorry, this is not theoretical. It's also fun and games. You can actually encode problems and make it useful for you. And if the time permits, I will go all the way down to Teseitin encoding, where I will try to show you that the conjunctive normal form, as on the surface, looks daunting, and it looks like turning problems into this form is non-trivial. But somehow this thing comes to our help with some cost, and we will discuss what is that cost is. Okay, so I hope you understand this plan, and this will prepare you, in my opinion, for understanding what comes next. Uh, okay, so what is the satisfiability problem? Okay, so let's start with something simple. Okay, so let's suppose you have two variables x and y, and they are rational variables, and choose a value of x and y such that the following formula holds true. Can you tell me what will be the value of x and y? You can type your answer. There's nobody who can tell me what's the value of x and y. Oh, yeah. So some said x is equal to 1, y equals to 2, but there are infinitely many choices. But naturally, we will choose. So I'm saying rational variables. X and y are rationals. Okay, so there are infinitely many solutions. In fact, you're thinking four solution means you're thinking only integer, I suppose. Yeah, and positive integer. Yeah, negative values are allowed. Yeah, of course. Why not? Okay. So until stated, yes. Yeah. So how do we write it? We write it in this following form, in which you have x equals to 1, y equals to 2. We basically say that x is assigned to 1 and y is assigned to 2. So this notation may not be uniform across several presentations, but generally you write this thing which we call model, and that satisfies. This is called satisfying symbol, and x plus y equals to 3. Okay, this thing called formula. Now you can do, like, if I can give you a model and if I give you a formula, you can answer this question, which is called evaluation of a formula. So we will, that's like the example we just saw. And for example, we can say that equals to 1. You can say that, oh, does it satisfy x greater than 0? Does it satisfy or not? Please answer. Yes, satisfies. Okay, so it's very easy to say. I mean, it's just this is the very simple observation, just for fun. You keep the okay. What about the next one? Does it satisfy? Yes or no? Yes. Okay. Yes, a lot of yeses are following it. So this thing satisfies. So now let's look at the next one. Okay. So does it x now it satisfies or not? Now from the pattern you can see it's no. Okay, so machine learning it doesn't work. So yes doesn't mean always yes. Okay, so yeah, sometimes it doesn't. So you can evaluate. Okay, so the furthermore you to observe is that it's seemingly very easy problem. If I give you the model and I give you the formula, you can easily. So this is very much evaluation. It's simply executing the formula structure. It is not expensive task. However, if you have a difficult question, which you can say that if I give you just a formula and give me a model, okay, and then your model is not given to you, yeah, so you need to find the model, okay, is far harder problem than the problem we just discussed, okay, and and so now let's say x plus y equals to 3, x greater than 0 is what is it? Can you give me a model? Oh, sorry, you don't need to find a model. I can just say it's SAT or not. Yeah, is it SAT? Is it SAT? Yes, it's SAT. Now let's look at x equals to 3 and x greater than equal to 0 and y greater than 10. Can you tell me why this is unsat? Like, how do you reason about it? You can type a quick answer. Somebody can. Why would you say it is unsat if you say so? So yeah, so x plus y get equal. Okay, so yeah, so the one way of so there's a way to argue about it. Yeah. So like somebody wrote, there is a no positive x for y greater than equal to 10 satisfies equation. Okay. So this is this idea is simple that we in arithmetic we do it all the time. But this can be formalized and turned into an algorithm, and that algorithm is called simplex. Okay. So basically y is too large. That means x has to be very small. Okay, because x plus y has to be 3, and since x is bounded by 0, it cannot be made. Cannot be satisfied. And the algorithm that implements this idea is called simplex. Okay, so what about this formula? Right? Does it have a satisfying assignment? Yes, this is SAT. And I just introduced a new symbol, which is called disjunction. Okay, so if you don't recognize the symbol, this means either this or this. Okay, and this has been conjunction so far. I hope I did not introduce it. But there's another thing about this, like no matter what value of x you choose, it's true. So this is not only SAT, it is more than that. Okay, so that thing is called valid formulas. Yeah? So valid formulas are those formulas which are always true. Okay, so now I have sort of give you some context to what is a satisfiability problem. Now I want to give you something more. Okay, as it's like not all satisfiability problems are made equal. Okay, so some set problems are easy, some are hard, and then even harder. So let's see what are these problems are there. So we saw this x plus equal to 3. You gave the answer very quickly. Then I made it slightly harder. I say y greater than the 10. Then you also gave the answer. When I said x greater than 0, then you said you have to think a bit, and you said, oh no, it's an unsat. And you had to reason it out, right? So this process is one type of problem. Okay, let me make it even harder. This problem. Okay, Now, can you tell me a satisfying assignment now? Or is there any? Let's see how quickly you answer. So one thing to realize is you need to have a case split. Okay, so you need to think a bit. I don't remember the answer here. Okay, so you have to think a bit, and you have to make us solve with this case. If that doesn't work, which was the case here, then you have to try this case. Okay, and maybe this case will work. Okay, and so there's a case split. So the if both conjunctions and disjunctions appear, the problem gets observably hard. Okay, and let's make it even more complex. Okay, what if I put in quantifier, and now I'm saying give me, so see, in this formula you have two variables, x and y. One is quantified, so I'm not asking you the value of y anymore, I'm asking you the value of only x, and I'm saying give me a x such that for all values of y it's true. Okay, is there an x? Okay, maybe or maybe not. Some people are saying SAT now. Okay, so can you give me what is the value of x? Can you choose the value of x? I mean, you need to give, you say SAT, I mean, you need to provide me evidence, right? Okay. Oh, somebody says unsat. Okay, now we have a dispute. Okay, so I don't remember again the answer, but if it's unsat, then you need to argue. Okay, but anyways, that's not the important here. Okay, so since we have a dispute on answers, okay, or maybe then you can tell, it can somehow demonstrate that things got harder. Okay, so now let's get to the terminology. As I said, not all problems are made equal in satisfiability problems made equal, so there are levels of hardness. Okay, so first class which I discussed, it was called theory formulas. Okay, and in this theory formulas, you have the situation that you only have conjunctions, and you have this theory atoms. The theory is, I mean, then let's see what's a theory is. Theory is a subject matter. Like in this case, your rationals, maybe it's a Boolean variable only, or maybe it's talking about arrays, or maybe talking about pointers, whatever subject matter is. Okay, so that is your called theories. Only the subject matter is involved, and the only conjunction is involved. Okay, then you call it as a theory formulas, and you can solve them. And we have been solving this formula for a long time. I mean, 50s, 60s operational research and linear optimization has been doing this, and it's been very successful technology. Okay, now comes this, now we introduce both conjunction and disjunction. Okay, and now this class of formulas are called quantifier-free formulas. Okay, I mean, it is actually absence of quantifier is being said, is a sort of negated sentence, negated phrase, but that's the terminology. Okay, so it's called quantifier-free formulas, and the hallmark is that disjunction and conjunction both should be present. I mean, if either of them are missing, then you say no, it's still fall back to the theory problem. Okay, and you want to find a satisfying assignment. Okay, so now the even next level is you also include the quantifiers. Okay, and almost all mathematics, I mean, not all mathematics, but most of the mathematics that potentially interest you can fall into here. Okay, there is mathematics which are outside of this, and second order logic, third order logic, higher order logics, but let's not worry about in this lecture, and at least in this whole 3 days, don't go there. Okay, so so maybe quantifiers will show up somewhere, I don't know, but probably most of the discussion of this today, at least today's discussion, well, I will just I will discuss what is today's discussion, but I will don't worry about beyond these three classes. Okay, so first class, generally, I mean, it's not easy means if you x and y are integers, is actually a hard problem. But if you have only theory formulas, then it's a relatively easier problem. And now once you introduce Boolean structure, which is conjunction and disjunction, then you get a hard problem. And if you introduce quantifier, it gets very hard. Okay, I'm not using the formal terms here, and people who are vetted in the complexity theory can actually can say that what can X be an expression in the model? No, no, no. You need to model only takes constant values. Okay, so you cannot have expressions. Okay, so you cannot write in terms of. So what you are thinking is quantifier elimination. So you can have a procedure which allows this kind of substitutions, and at the end formula reduced to false and true, and thereby you know that formula is satisfiable or not. And for one big simple example is Gaussian elimination. You must have done in your high school. When you have sum of two children is 3 and difference of their age is 1, then what are their ages? Okay, and you solve it by eliminating variables, right? So this is called Gaussian elimination, and there you are substituting, and you may be saying, oh, that's the process I do, but where's the model? Actually, model gets constructed in this process. You basically I will not get into that. Let's not extend that discussion, but you can see what I mean. Okay, you model only have concrete values. Okay, so this is the business. Okay, so now let's zoom into quantify-free formulas. Okay, that's the most interesting bit that this whole this school is about. Okay, quantifiers, they are coming into the play, and a lot of tools are out there which are doing quantifiers, but I think this is not the focus of this particular version of the school, and maybe I'm wrong. Maybe I have not seen all the content going to be covered by the other speakers, but somehow somebody may do quantifiers. So forgive me if I say. So I only focus on quantifier-free. Okay, so so you have a theory atoms, right? So you basically do the theory atoms Boolean, and what is the thing is that you have a theory atoms in the Boolean structure. Okay, that's what happened. Okay, so this already have discussed in a quite in this. Okay, so now the propositional formulas are special case where the theory atoms are Boolean variables. Okay? So let's simplify the formula, not simplification, but spatialization. Okay, so instead of theory atoms, which we had P1, P2, P3 are Boolean variables, they take the place of the theory atoms. Okay, and they take values 0 and 1 only. Okay, and then you can use normal proposition logic to evaluate this formula. Okay, so if this formula given to you, you can say that P1 assigned to 1, P2 assigned to 0, P3 assigned to 1 is my satisfying assignment. Okay, and this is called proposition formulas, and they are special case of quantifier-free formulas, which I discussed. Okay, and actually this is the call when you solve these constraints, you call them SAT solver. Okay, so here is a jargon. Okay, so some people tell you I am building a SAT solver, or here is a SAT solver. So what it does, it only solves this propositional formulas quantifier-free. There are no quantifier allowed there. Okay, and no other types of variables, only Boolean variables. And you can take their conjunction, disjunction, implication, whatever combinations, Boolean combination you can do, and you solve them, then you call that SAT solvers. Then what is an SMT solver? SMT solver is quantifier-free formulas. Okay, now you can allow to write any arbitrary atom. Okay, for example, I showed you x plus y equals to 3. That kind of atom you can write in your formula, then you call SMT solvers. A quintessential SMT solver does not solve uh, uh, quantified formulas. However, that is not true. Okay, today the major tools like Z3 can solve quantified formulas, but that's a sort of a misnomer. Like, I mean, now you should call them theorem provers. Actually, they are transitioning to start calling it theorem prover, because now they are not just solving quantifier-free versions of the formulas. Okay, so the SMT stands for satisfiability modulo theory. Okay, so satisfiability is sort of referring to this world of SAT solving. I say, oh, I added the theory. Okay, the way I have told the story that you build a generalized formula and you remove the theory and you left with SAT solving, but typically the phrasing goes that you have a SAT solver and you adding theory on it. Okay, so So that's this called SAT solver and SMT solver. So today Arvind will go in depth how the SAT solver works. That's not my topic. I'm not going to discuss how these things work at all. I'm just going to show you how potentially you can use it. Okay. Okay. Let's say theory solvers. SMT solvers are divided into two components. SAT solver, it solves the Boolean constraint, Boolean structure, and the theory solver, it solves the theory constraints. And somehow their synergy makes it work. Okay, and that synergy is called SMT solver. Okay. So, for example, as I alluded that in this case, this formula which we have been seeing so many times, you have unsatisfiability, and to argue that this is unsatisfiable, you need to use linear rational arithmetic reasoning, and specifically the algorithm that is commonly used by the solvers is simplex algorithm. The important comment to made here is a simplex algorithm itself is an exponential algorithm. By theoretically, it should take a worst case exponential time. And even then I said it's an easier, okay, than doing doing the Boolean structure reasoning, which is also of same complexity class. So why I'm saying this is easier? Because what has happened in the practical experience, people have found that simplex is far faster than the theoretical predictions. Okay. And now they have been proven that very high, if I give you a linear constraints over rational numbers, very high probability that almost one probability that it's a linear time algorithm. And that's a weird statement. Suddenly you jump from exponential to linear. In practice, that's not even observed. You don't observe simplex running as a linear algorithm. Neither you observe it running as exponential. So what is going on here? So now that some complex notion of theory complexity has come into play, and we now understand how simplex algorithm behaves. If you are interested, I can give you the reference. Okay. So that's why I'm not using any formal terms of using for complexity theory, for example, NP hard, NP complete, exponential, polynomial, because once you start going to solving, they don't start, they quickly break down. Okay, so let's avoid those terms, at least in this discussion. Okay. Okay, so I have.
So Ashutosh, I think there is a question.
Let's not do that again. Okay. Okay. So now let's zoom in our focus on the SAT solvers. Okay. What are the SAT solvers? Well,
Hello.
find ourselves. SAT solvers were solving Boolean formulas. And how do we solve them? Using conjunctive normal. Sorry. How do we solve them? Using some algorithm. Okay. Oh, sorry, I missed this message. Is this what we call integer programming? Uh, I suppose, yes, I think you are pointing to the simplex. No, simplex, when you solve simplex, then you're doing rationals. Okay, the integer programming is on top of simplex. You have a constraint that variables cannot have a fractions. Okay, so then you do something more to it, and that is just not simplex. There's something simplex plus plus, you can say it, and that is much harder program. So that's called integer programming. Okay. The Okay, so why you want to do normal forms? Why you want to say that give me all the formulas in a conjunctive normal form? Okay, first of all, if I give you arbitrary format of formulas, it will be difficult to implement, and suddenly you start doing PhD. You say I want to build a new SAT solver. Suddenly you have the daunting task of parsing all the possible input formulas somebody can generate, and the formats can be many. So we need to all agree that what should be the input. Okay, not only a file level, okay, what syntax I will provide, also conceptual level, what kinds of formulas I'll provide. If I can cut down the syntax and notation, then it's much faster. And if there is a convenient notation, let's use it. Okay, so there is a convenient notation, and that's where I will go to. Okay. Okay. So what will happen is, if you generate a formula, if you want to give it to SAT solver, first you to turn into a in normal form. Okay, so that normal form is called, in this area, is called conjunctive normal form, and we will discuss that. Okay, so before conjunctive normal form, there is another step you need to go through. It's called negation normal form. So first I will define what is a negation normal form, then I will say what is a conjunctive normal form, and I will then we will see then how it's used, and I will show you an example where it's actually very useful. Okay. 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 So first of the, so we have a three ugly operators. Okay, which is called implication, XOR, and equivalence. Okay, and they create a lot of problem if they show up in your formula. I mean, actually the implication is not a serious problem. Okay, so if you have implication, it actually means not P or Q. Okay, so this is almost, you are in the world of conjunction disjunctions, is not leaving. Actually it's actually sometimes it is the fundamental operator. Okay, so these two operators create a trouble for you, and so if you want to turn into conjunction disjunction only, then it creates actually a blow up, sort of a blow up. Okay, and equivalence is actually it can be encoded in XOR or other way around, but you can see that if you have any of these showing up, they will blow up. There is a there is a way to avoid it, but I'm not going to discuss that again in this presentation. And we assume that you have removed all of them. Okay, and let's assume that you only working with conjunction and disjunction formulas. Okay. Okay, so let's see what is negation normal form. So negation normal form is very simple. Only propositional variables have a negative symbol. Okay, for example, you're not allowed to write that P and Q. Okay, this is not allowed. Okay, so we know that you can easily push negation inside. I mean, negation pushing is like first thing you learn. Okay, in propositional logic, and any operator you can push negation inside. Right, you can just write whatever, you can always do that, and therefore you can take any formula and can turn into negation normal form. Okay? So that argument is fairly simple, just push negation inside. Okay, let me go over an example such that, if anybody who doesn't know gets clearer image what happens when you give the formula and solver does the negation normal form. Okay, so this is you want to do the negation normal form, and first you just push not inside, so then this is implication shows up. Okay, so implication turns into conjunction and Q stays the same, and then not comes here. Okay, so this this is standard transformation. P implies Q can be transformed into what P and P and not Q, right? Okay, so then this negation has to push again, and if put negation sitting on top of XOR. Okay, so how do I do that? Trick is that you negate only one of them, not both of them. Okay, so that you should remember. Okay, uh, XOR is basically disequality, right? So if this is not equal to this guy, if you negate it, you basically flip the one guy. Okay, now this guy is not disequal to this guy, or you have other option, you just flip this sign, you make it equal, right? Equivalence. Okay, so this is your choice how you want to transform it. Okay, then you push this negation again inside, and then you left with, now you have a only negation on top of propositional variables. Okay, you may call it a negation normal form, and some people say no, it's not a negation normal form, because you still have this XOR setting here, and XOR has a negation hidden inside it. So if somebody really says that give me a negation normal form, it actually means uh, uh, why. Okay, so okay, this my phone is turning off, and then again I'm not able to see the question real time. That's my mistake. Okay, so why we cannot okay, let me finish this discussion. I will answer this question of Fahd at the very end. Okay. uh, Okay, so yeah, so there are integers hidden. Sorry, there are negations hidden inside these symbols. So some users would say that get rid of them also, then only you can call it NNF, and some will say no, no, no. Depending on the tool and different on the implementation, there is no global standard what means NNF. Okay, different. That's at least that's what I understand. Okay, so don't quote me on that. Your definition of NNF doesn't meet with meet with exactly what is written in Wikipedia. Okay. So, but you got the idea. Okay. So this is typically assumed that if I give you a formula, first thing the tool will do, push the negations inside. Okay. Because negations are bad and just misbehaves like, you know, everywhere. So just push the negation to the booleans. Okay. That's the first thing you do. Okay. There is a slight involved thinking involved that you need to just need to think of a linear time algorithm to compute NNF. The algorithm you think what is a linear time, and what you find on Stack Overflow is not linear time, and it almost every time I give as assignment and student get it wrong. So just think about it. Okay. Um, Okay, so now let's get to conjunctive normal form. So now you have NNF. You don't have a negation anywhere on top. So Boolean structure, and let's suppose you have got rid of all other symbols. Okay. So so what is left? You have a conjunctions and disjunctions. Okay, nothing else left. And what? And you want to get into even simpler form. So let's see what I'm getting there. Okay. So before that, I need to have some terminology set up. Okay. So all the propositional variables are called atoms. Okay. And literals is either an atom or its negation. Okay. And a clause is a disjunction of literals. Since disjunction associative commutative absorbs multiple occurrences, you can simply say that we can interpret it as a set. The clause can be used as a set. Okay. So P, for example, just follow the definition, just practice. Okay. The P is an atom, not P is not an atom. It's a literal, not P and P, both are literals. Okay. And this is a clause. Okay. You can see P is repeating. You can write it as a set also. Okay. This is also a clause. So you can give a set of literals, not set of atoms. Okay. Notice that. Okay. A set of literals. So if you have n variables, you can have a 2n long clause at most. Okay. So you have a set of literals, which is called clauses. Okay. So what is a CNF? Basically, CNF is a conjunction of clauses. You cannot have, so only thing that is allowed to happen is you can have a conjunction and then below there are disjunctions. Okay. Okay. Again, conjunction associative commutative absorbs multiple occurrences. It's you can treat it as a set of clauses. Okay. Okay. So as let's look at it, not P and P both are CNF. They are conjunction of single clause. Okay. This is also CNF. Okay. And since a CNF formula can be viewed as a set, this is also a CNF formula. Okay. Now each clause can be written as a set. Remember that. So a CNF formula technically is a set of sets. Okay. Right. So this is, and that's how typically it's written. I will say this set, it belongs to this whole set. Or I will say that not R is a literal belongs to this set. So this set notation is often used when you're referring to clauses and formulas. Okay. So write a okay. So how can we represent true and false unique CNF formulas? Any ideas? We don't have explicit true and false symbol here, okay. All you can do, you can build these sets. Okay. Set of sets. Okay. You have a literals, you can put them in a set, becomes clauses. You can put them in another set, that becomes formula. So how do I represent a true and false using this CNF formulas? And you're not allowed to use explicit true and false. Okay. So what is that notation? How would you write it? Let's fix true. How do you write true? No. You need to stick to the, give me the, okay, P or not P. Okay, that's one clause. But do you have a simpler solution? Yes, somebody asked this question that what do empty sets represent? So we have emptiness, empty sets. So you have let's say you have an empty set. But how somebody said p, this is not true. I mean, if I give you p equals to 0, this thing becomes false. If you are representing it as a yes, so empty clause means false, no number means, no clause means true. Okay, so if I give you empty formula, this is equivalent to true. Okay, if I give you now, how, let's suppose this is a hint I have given you. Okay, now how do I represent false? Now somebody can give me false, and Karthik has made a point. So can you use Karthik's point and write down what is the representation of false? Yes, correct. So this is my right, correct. Okay, this is my false. Okay, if you so that basically what happens is, if you give you a bunch of clauses, okay, and you want to show that these clauses are unsatisfiable, you need to derive the empty clause. In your set of clauses, you want to introduce this empty clause. If empty clause is present in your set of clauses, then you have found evidence of falsehood. Okay, so that's the some play how things, how the algebra of say CNF formula works is needs that. Okay, okay. So due to interest of time, I will not go into detail how the argument of conversion to CNF conversion happens. It's fairly simple, that if you have a conjunction, conjunction, sorry, what, who's sitting on top who? Okay, let me say, yeah, if you have this structure, okay, if disjunction is sitting on top of conjunction, that's bad. Okay, so what do? You apply distributivity. Okay, so you distribute these things over these guys, and then you get an something which is basically swaps this conjunction to up there, and this disjunction goes down, and then you have a basically CNF. You're moving towards CNF, and anytime such offending relation is found, then you basically do the distributivity, and then disjunction will be pushed down and conjunction will be pushed up. Okay, and then how you get basically. Okay, okay. So eventually you will find CNF formula. Well, there is a catch here. Okay, so this is something which is you should think about, is that each time you do this swap, the formula gets larger, right? And you're not done yet. Maybe more offending things are somewhere, like, disjunction sitting out of conjunction, and they may get copied several times, right? So why would you terminate always? Yeah. So each time you do the, okay, here's an example I'm presenting, but main point is that, are we done here? Okay, that each time we do the swap, the formula grows, and you have to do more swap, then it grows again. So how are we guaranteed that this whole process is going to terminate? But intuitively, it's very clear that it must terminate. I mean, it's very obvious. If you stare at it, it says yes, it should happen. Okay, but the formal argument is slightly non-trivial, and I would encourage you to follow it up. Yeah, if you don't know it yet. Okay, so these are like when hidden things where it appears very simple, but its formal argument is not trivial. Okay. Okay, so okay, here I must, this slide is very important because everything rest of the day hinges on it. So unit clauses, okay, contains only one literal, right? Any clause that contains one literal, I'll call it unit clause. If I exactly two literals, okay, both can be false, both can be true, one false, one true, all combinations are okay. Binary clause. Ternary clause means you have a three literals, and there, three is very important number, and because every formula can be turned into a three clause formula, because you don't need a clauses longer than three. This is not, again, this is a very something you need to know. It's a complex observation, but that's why these three are specially defined in the terminology, and you will see that Armin and others will be using this terminology extensively. Okay. Okay. So I have given the intuition of this, all these empty clause, so I will not cover that point again. And Okay, here is a very important. So give a linear time algorithm to prove validity of a CNF formula. Can somebody give me that? So how do you say that a linear time algorithm to prove validity of a CNF? This algorithm exist? Do you have any ideas? How would you do that? Validity, what was the validity? Definition of validity said that all assignment must be satisfied. Okay. Okay. Yeah. So somebody said, Devesh said, okay, Devesh, you should not be answering my questions. Okay. Okay. So, no, it's okay. Fine, fine. Devesh is my PhD student. Okay. So, if, uh, yeah, so you don't need to look at all clauses together. You can individually process them. If any of the clause becomes not valid, then the whole formula is not valid, right? So you process them separately, and in each clause you want to know that it is valid. When if a clause is valid, okay, when a literal and its negation both appear, okay, then only it becomes valid. Otherwise, it rejects something. Empty clause is false, okay. Uh, right. So as soon as you keep it making longer and longer, clause accepts more and more assignments. And any given time, if you add a literal and it's a negation both in that clause, then it becomes false. Okay. So this is like, these are a few observations. When you make it, you are more comfortable with Boolean algebra. Okay. So that's important. Okay. So I said I was proposing, I was promoting CNF. So I said, why CNF is so interesting. Okay. And in fact, CNF is not universally accepted. If you go to if you've done your Boolean algebra, Boolean logic class in your electrical engineering departments, or basic circuits, you must have seen this Carnot map. Okay. And Carnot map actually does not produce CNF, it produces DNFs. Okay. It puts the conjunction first, and then they put the disjunction afterwards. And why they like so much basically DNFs, and why we like SAT solver people like CNF. Actually, there's no such distinction. Depending on your usage and situation, you prefer CNF or DNF. Okay. Uh, so let's see why we like CNF. Okay. So the when you trying to encode a problem into SAT encoding, okay, so you can translate hard problems into your SAT problem. Okay. And you have certain goals. You want to have a compact encoding. Compact encoding means what means is compact encoding? When you have a problem statement come to you, and it comes with, let's say, 1 kilobytes, then you should not produce in a SAT problem which is a 1 megabyte file. Okay. Some linear blow up is okay, but should not be exponential and very large blow up. Okay. uh, uh, yes, Karthik, yes, that's the answer to your question. Yeah. uh, Redundant clauses may help the solver. Okay. So it's not the case that you only precisely encode the problem. You sometimes add extra information. You can give more information. For example, somebody wants to go from here to Delhi. You can also tell them about the most efficient road. Also tell them, there's a side roads. If that one is blocked, you can go that way. Okay. May not be useful immediately, but maybe that extra information helps somebody to find a better way. Okay. Uh, Secondly, you need to encode in a way that is compatible with the CDCL. Now, what is this new term has come up, which is called CDCL. CDCL is the algorithm that is inside the most of the SAT solvers, and probably Armin will going to get into depth what CDCL is. So you want to be in code which is compact, maybe some redundant information, and we have to be compatible with CDCL. Okay. And that CNF fits the bill. Okay. What happens is most problems comes as a sequence of restrictions. What is allowed. Okay. And this restriction comes in a particular form. If certain situation hold, then something else must happen. Okay, so this is natural implication. Okay, an implication naturally is CNF statement. Okay, so if I give you P implies Q sort of formula, and then you say, okay, not, it can be translated into not P or Q. Okay, assuming both are Boolean variables. Okay, so these are natural sort of choices. Okay, so to have CNF. Okay, and then you put several restrictions, so then they fall, come together as a conjunctions, so they are naturally in CNF. Okay, so so this is a famous quote by Davis and Putnam, who invented DPLL, again going to be covered by Arvind probably, and that is saying that CNF is a good format to handle. Okay, so I okay. Okay, let's try to convert a problem into a CNF encoding, and let's say we color a graph. Okay, and with at most D colors, such that if edge is there, then nodes along the edge should not have the same color. They should have a different color. Okay, so how do I encode such a thing? Okay, so I will do some sort of SAT encoding. So how the SAT encoding proceeds? First, you need to choose the variables. You need to choose what variable is going to represent your problem. Okay, so you choose in this case we will choose variable Pij. Okay, variable Pij says that if for I node and the jth node, Pij, sorry, no, if I is the node and j is the color, then Pij is true if Vi is assigned jth color. Okay, so this is my variable. Now what I will do, I will create clauses. Remember that I will create CNF formula to encode my problem. So first thing I will say that every clause, sorry, excuse me, yeah, so each vertex has at least one color. Yeah, so you can, so one of these variables, which is for each I, you create one clause. So for our pi1, pi2, pid, one of them must be true. Okay, that's how you assign the color. If there are two nodes connected by this edge, some edge, so vi and vj, then for each color, okay, so just look at this thing, for each color have to make sure both variables should not become true. Same color is not assigned in both the nodes. Okay, so for each edge I have to create this about, let's say, d clauses. Okay, so the d clauses for each edge, right? Size of edge times d. Okay, that many edges will be added. Okay, now you can naturally see that this guy is a clause, this guy is a clause, and they are put together as a conjunction. So therefore you have CNF formula. Okay, now question, why am not encoding every vertex has at most one color? Look, remember that I just said at least, and I'm asking you to give color. So color giving, when I say give a color to a node, it means I'm saying one color. So why am I not, and I'm saying I'm done here, sort of. Actually I didn't say it, but I'm saying it now. I'm saying I'm done, I don't need to encode more. But in a keen observation, observer will see that I missed something, and my claim is it's okay, I don't need to worry about it. Can somebody say that why that is the case? If you want to comment, please. I will. Hello. Please let me see if somebody's typing. So why I don't need to say at most one color? Right. So somebody said yes. So if my method, okay, so the answer is correct, right? At most one allows 0. Yes, yes. At most, yes, yes, you can say. I said at least here, so if I say at most, then it means yeah, it allows zeros. But if both them together will say exactly one, right? So it has said already one, so it's okay. So yes, so the second last comment is correct. Is that if this problem you solve and it assigns two color, let's suppose pi 3 and pi 4 becomes true, then what do you say? Oh, well, two colors I can color it. I can choose any color. And the way the constraint has been solved, no neighbor of the ith node must have 3 or 4. Okay, so done, you're done. So right there, you see that if you were naive, then you would have encoded this guy. But this observation allows you to have a simpler encoding. Yeah? And it's not the case if you encode this, the solver can automatically recognize this is useless thing and I can ignore it. Solvers are not that smart. So encoding can have choices, and even in very simple settings, you can get choices. Okay, so it is not so immediate that you get a problem and you immediately get the encoding. Okay, so it needs some thought. Okay, so then now let's run this thing on a solver. I'm not sure that solver did. Oh, solver did start. Okay, yes. Okay. So do you see my? Just want to confirm. Do you see the program written there? Yes. Okay. Okay. Just let me make sure. Where am I? Okay. Right. So let's look at this code. Okay. This code is doing exactly what is being said in the earlier. So what I'm trying to do here is I have a graph which has 500 nodes, and I want to color with 3 colors. Okay. And edges are stored in some edges file dot, let me show you edges.txt. Okay. Some edges file. This is a randomly generated graph. Okay. Right. So this graph was generated randomly. Now what is happening is I read these edges from the file and stored in some vector edges. Okay, so let's see. Okay, now I'm going to do, I will encode the problem and consider, let's say, first 3000 edges and try to color it, then add 40. This is next one, the next, and then 3040 edges, and then try to color it. Then I add more 40 more edges and then try to color it and see how much time, how much effort it takes to solve this problem. Okay, is it like, so far what I tell you, like, is this size problem is tractable by modern SAT solvers? This question should come to your mind, right? So let's first I need to choose a Boolean variable for each node, each color. So this is if you don't know Python, don't worry about it. Basically, this is a constructor which creates a Boolean variable for each node and each color. Okay, so then what I need to do, I need to create a clause, which this thing creates a clause, or of these variables stored in this vector. Ith node, we have d colors, right? So VSI is a vector of all the color variables. So you just take an or of them and put them in this node constraints. Okay. Now I have edge constraints. Okay, what are the edge constraints? In these edge constraints, what I'm seeing here is that you, for each edge, same idea goes, that you pick an edge. Okay, and you say my edge, one end of the edge is E0, other end of the edge is E1, right? Pick the corresponding variables for color J. Okay, right? So J color, both sides have J colors. Okay, and I'm picking J. Okay, and both should not be true at the same time. Okay, and I'm taking a OR. Okay, and I keep adding them. Right. Okay. So then what do I do? Then I have stored all these constraints in my store, and then I will do is I will uh, I will add these constraints and solve them. Okay, using the solver. Okay, and the solver has some sort of a constraint that it adds only certain number of constraints related to certain number of edges and then skips ahead. Okay, and then it solves them. Okay, so let's, since I am running out of time, let me not go over the code in step by step. Let me run it. Okay. Okay, if I did find it. Okay, where is it? Where is it? Mini projects. Yes, CD SAT. Okay, so let me run it, and what is graph color.py? Yes. Okay, so you can see that it's running, and it considered 3000 edges and solved them. You see, it took some time, and it gave you SAT, right? And start adding more and more edges and start solving them. Okay, at some point of time it got stuck. Okay, like for example, you can see that the 3440 edges uh, was solved in let's say 1 second, and now its next attempt is 3000. Every step is 40 off, right? So 3480 edges. So it is getting stuck. So let's hit run and see what happens. Okay, so let's get back to the presentation. If I where is, yes, okay, I will take 5 minutes, okay, to finish. So let it run and we will come back to it. Okay. Okay, so this is a final point I want to make, and I will not go in depth, but I will give you the intuition. It is a 5-minute intuition, and it should be very clear from itself that this by intuition. Okay, so transformation of to CNF was via distributivity, which explodes. Okay, and which is a very bad idea to do. And not all problems will won't give you CNF immediately. I mean, they're like, if you go to cryptography, it just won't give you. Okay, it's had a lot of XORs in it, so actually it's even a bad idea to do that. Okay, so so there is a way to not do this explosion, in short circuit that, which is called Teseitin encoding. If you can hear it, my laptop is hot now. It is fan is running at full speed and SAT solver is running. Okay, and there is a cost of doing Teseitin encoding. Okay, so let's see what is the cost. Okay, so let me give you one example. This example will make it crystal clear what Teseitin encoding does and why it avoids the cost, and it adds some at different kind of cost to your problem. Okay, so let's see. Let's suppose you have this formula, which is not a CNF. You have a disjunction sitting on top of a conjunction. So I want to convert into CNF. What do? You replace offending term. Okay, this of what you call offending term, the term which is sitting under the disjunction and which has a conjunction in it. Okay, by a fresh variable. Okay, so I add a fresh variable there. So, but that's not it. I mean, you got rid of, I mean, how does it X relates to Q and R value? You know, somehow you need to connect them. Okay. So what you need to do, add clauses to encode that X behaves like Q and R. Okay. So how does this happen? Okay. So my original goal was to make this clause satisfied, right? This formula satisfied. So if I satisfy this by making P true, okay, I'm done. Okay, I don't need to worry about Q and R values, right? So X, I did not to worry. But let's suppose P is false. So how else I can satisfy this? Making X true, right? If I make X true, then what happens? Then I add this thing. This thing says if X is true, then I have to make this one true. Okay, it's only one way implication. Okay, so it says Q and R must be made true. So this guy turned into CNF, but is this part in CNF? I mean, this doesn't look like in CNF, but worry not. Okay, you can simplify this. So X implies something, implies conjunction of several things can be turned into this form. Okay, X we know is a variable. Okay, because you just introduce a fresh variable, so you can write into a not of X. So this not negation won't introduce sort of another trouble for you. And it stays in NNF form and CNF. Okay, and this gets split up. Okay, so you got Q and R, right? Yeah, so you get this. Now this formula is in CNF. Okay. Now the question. Okay. We should have introduced ideally x equivalent to Q and R. I mean, I'm saying the what statement says that X behaves like Q and R. Okay. So that means actually that sentence implies that X is equivalent to Q and R. Why does the above with implication works? Like how I get away with not writing equivalence? Anybody has any comment on that? And will it work always? Are there situations when this implication won't work? Any comments? Let's see how the SAT solver doing. Wow, it's taking a long time. Okay. So yeah. So this is the, if you read Wikipedia and standard sources, they will be using this equivalence. Okay. But the reasoning says that, okay, I don't need to really write equivalence. I can just get away with one direction of implication. But there are situations when this implication doesn't work. Okay. So what are those situations? When you have a P or Q XOR. Sorry. No. Sorry. Undo. Okay. This is not the case. P XOR. Let's say Q and R. Okay. So now this term is sort of this term is cannot be taken out, and you can just write implication. You have to write equivalence, because like when I made P true, I didn't care about the value of X. Okay, but in this case, if no matter what value of P you choose, you care the what this produces. So therefore, when you replace by X, it doesn't work. You need to really solve it. Okay. Okay. So this is amazing. So now let's. So this ends the discussion on the Titan, and amazingly, it's supposed to finish now, because I've been early in the morning. I ran it. It finished by now. Now it's not running. Can anybody has a guess why now it's so slow? Because what may be the guess? And can anybody? Uh, Not necessarily. Not necessarily. SAT checks are also. First, can you give me the intuition why the SAT, as I considered more and more edges, the SAT, why switch from SAT to unsat? Can somebody reason it out? Yes. So as so as you add yeah, so so as you add more and more edges, coloring becomes harder and harder. Okay, so then some point of time you will not be able to color anymore. So adding more edges means you will go from sat to unsat. Okay, so that is the nature of the problem. Okay, not all problems are like this, but this problem happens to be like this. But anything, another thing you notice, just came out 3680, and it took 30 seconds. And and look at 3480, like 4 5 entries ahead. Oh, time is getting smaller and smaller. Can somebody tell me why now time is going down now? Do we really need to run beyond 3 when the unsat has reached already? We are not. We are not. each time we are doing a different query. So each time the solver is restarting for each query. It's not that like you solve it and then you go to the next step. And you don't do incrementally. We are just testing the SAT solver, how the SAT solver performs. Okay, so if I give you some problem and how it is going to perform. Oh yes, that's the graph I was waiting for. Okay, so one reason why this solver I think got slow because of I'm doing the Zoom call at the same time. So I think some resources are busy there. So you can see that things get slowed down. So you can see that the green line is there was a SAT. The green line says whenever, and then suddenly it becomes unsat, and then there's a peak, okay, around the transition, and then timing start going down again. Okay, can you explain it why? Why that is, why it becomes easier to prove? Degree is increasing. What do you mean by degree is increasing? Nodes have degree greater than D. Oh yeah, nodes. Okay, okay, okay. But not uniform. It's a random graph, right? I mean, yeah, it's increasing. Some point of time, yeah, but but why? Yeah. So what happens is that think about like when, let's suppose I want to three color. This is a three color problem. As soon as there's a click of four nodes, okay, four nodes all connected with each other is found, it is unsat, right? So if you add more and more edges, the probability of finding them gets higher and higher, and then you get unsat, right? And that search becomes easier and easier. So over time, the depth of the reasoning, you assign this color, that color because of that color, and the length of the reasoning you need to go across the clauses to find a contradiction gets shorter and shorter as you add more clauses. Okay. Okay. So one observation is this, and if you kept on running, the problem would have been become easier and easier. Okay. So if I give you now the next question. Yes, yeah, Vishal, you are correct. Okay. So now the next question. This peak came around 3050. Okay. This is I basically I chose it carefully. Uh, However, the point is key why this peak came here. Okay. What is so special about it? Okay. Observable, actually let me answer it myself, because it's a transition era. Around here transition happened, and it doesn't mean the SAT is easier. If you had run it very more finely, you may have find out some SAT problem also took very long time. Okay. Um, but you can see that I had 7,000 edges. I started from very long one. I started 10 edges, 100 edges, 1,000 edges. I still was a SAT. Okay. And problem remained easier. And in a very narrow area, problem was hard. Okay. From 3,400 to let's say 4,000. Okay. And again, the problem became easier, very easy to prove on SAT. So if I give you a random graph coloring problem, most likely it is be easy problem. No? Why? This observation suggests that. Okay. What you can do, go try this. Okay. Try generate several random graphs. Okay. And try to check satisfiability and see how many edges later you will get unsat. And you will find that finding a graph in which this peak even shows up is difficult. I had to generate these random graphs about 1,000 times, and then I found this one graph where this peak shows up. Otherwise, peaks are very small. Okay. Okay. So there goes your complexity theory. Okay. That's why you may say SAT solver works. Okay. Or maybe do not work. Okay. So whenever SAT solver works, when that means the problem, most problems you will find of that particular subject matter are easy, and they are very hard problems in some corner hidden. Maybe you will, and that's where the hardness is. But real world problems don't lie there, so industry can use it, and likewise. Okay, so this ends my presentation. If you have any question, you can ask. You can please send me. You can write the questions. No questions?
So if there are any questions, we request you type in the chat. Hello, Ashutosh, can you hear
Yeah,
me?
yeah.
So,
Yes.
so there is one question you can see in the chat.
Oh, sorry. I switched to several. Yeah, we need to learn how to deal with these things. Can we? Why can every problem be transformed to three color problem? Every problem be transformed? I mean, no, no, no. I'm not saying that. I'm not saying that. Three color problem can be converted into a sad problem, and you can see that in the three color problem world, there is a very narrow space where things actually hard. Okay, this is just an evidence. I mean, this is not a formal proof, but it suggests something. Okay, and but SAT is a quintessential hard problem. So everybody translate into SAT rather than to three color problem. Since you can unmute people also. Since hard problems can be converted to SAT, and you show the pattern that most instances of SAT can be solved cheaply. Does it imply that most tension hard problems can be solved cheaply as well? No, no, it doesn't imply. There are problems which cannot be done. For example, if that is possible, then so you will crack any password out there, right? So what happens is that your password is stored in servers as a hash key. Okay? And so if I get hold of, so if somebody attacks a, let's say, Zoom servers and stole the all the hash keys, they still don't have your password. Okay, so they you need to revert the hash function to really get your password, and that is a sad problem. You can actually encode into SAT solver and solve it. If that is the case, that most the satisfiability problems are going to be easy, then you would have breaking all the क्या कहते हैं, you passwords, but that is not the case. So there are constructed functions, constructed problems. They are designed in a way that all the instances, most of the instances will be hard. So they are really hard problems. Okay, and but in complexity theory they will all look same. Okay, so they're all exponentially hard, but there's some problems have this nature that in theory it looks hard, but most instances they're not hard, and that's where SAT solver are winning the game. They are showing, oh, we can solve this hard problem, that hard problem, and not really. They often get stuck. Okay, so if you really, I can show you some instances, like very small instances, no SAT solver can work. Okay, so that's also true. Yeah. So let me see. Why Turing clause is sufficient for any problem? You mentioned in one slide by giving definition of oh yes, yeah, I said is there a way to predict peak of the graph? So the first question, okay, I have several questions. In the okay, so is Titan encoding you make use of implies the additional variable? Doesn't it add to the blow of the variables? Yes, it adds the not only it adds the state space because you have more variables, and also breaks the equivalence. The new formula generated is not equivalent to the original formula. Okay, that's you should note. Okay, and it can create problem in some situations when you are using as a sub oracle to do something else. Okay, so where the number of variables matter. Okay, so that is also a problem. Okay, so yes, it adds. So I said it. It saves something, but it creates other headache for you also. Okay. No, there's no way to predict. Oh no, yeah, yeah. There is a way to predict the peak. Okay, so there is a theorem in random graphs where if I give you that there's certain ratio between edges and nodes, then the probability of the random graph to be colorable suddenly sharply falls in certain point. Okay, so before that it is very high probability is SAT, and the ratio there's some number out there. Okay, so so that is predictable. Okay, so that is like random graph. Again, the random graph is not the way to test SAT solvers. Random problems usually, not interesting. Okay, the real world problems will not be random. They will have some structure in them. Okay, so uh, so there's no way to predict the peak. Okay, uh, in a real world situation, but in a random graph, yes. Okay, why ternary clauses is sufficient for any problem? You mentioned in one slide giving definition of the binary. So, so why? Because every long clause can be converted into a shorter clause. Okay, so let me show you how it can be done. Okay, so let me find a clean slide. Okay, so if you have, let's say, P or Q, or let's say T, let's say, so you can, what you can do is you can oh no, it's also ternary. So okay, so we need to add one more. Okay, so let's say T or X, let's say. Okay, so I want to turn into two binary ternary clauses. I will do this. I will introduce a fresh variable and split here. Okay, I say P or Q or X, let's call it Z, actually fresh variable Z, and then you say conjunction not of Z. Okay, or T or X. Okay, so now what I will do, I introduce a fresh variable Z which split the clause into two parts. And now, so what you can do, every long clause you can split into two parts. Okay, and these are both are equisatisfiable. If this is SAT, then this is SAT, or but equivalence is lost because of this fresh variable. Okay, so this transformation can turn all the long clauses into short clauses. Okay, but it cannot work beyond three. So you cannot bring from three to two. You cannot do it. Okay, and that is one of the fundamental problems. Okay, of sort of NP hardness business. Okay, because two SAT, if you have only two literal per clause, then it's an easy problem. It can be solved in a linear time. But if you have a three literals in a clause, then it is an exponential time algorithm. Okay, and more than that, you don't need to worry because everything else can be converted to three SAT. Okay, so yeah. Can the sequence of clauses affect the SAT on SAT time? No. The way it happens is in the SAT solver, which Armin will cover in depth. It gets stored in a data structure. Okay, and the data structure design is so efficient way that everything gets jumbled up. Okay, so actually the order of the clauses, the way you gave to the SAT solver, most likely SAT solver does not respect it. Okay, however, it strategizes how to search the solution. Okay, which I think Armin's business. I will not get into that. So wait for it. Ask the same question to Armin and he will answer you. To Gaurav, I'm saying this to Gaurav. Okay. Uh, Mridul, how to quickly identify the SAT solver doesn't work for some problem? Uh, I don't know. Just encode it, solve it. Okay, and that's how this is that's my bread and butter. I mean, some biologists come to say, I want to solve this problem. Then let's encode and see what works. And most of the time, it doesn't work. Okay, so that is the most of the business in there is SAT solver figuring. Let's suppose you have a hammer. You want to figure out which nails it can really push in, and you will find most of the nails it won't work. Yeah. So yeah, that's how the things are. Okay. Any other questions? If any clause is false, then complete unsat is found. So can we benefit from parallel programming for SAT? Oh yes. Parallel SAT solving is a big business. I mean, big business is a big area of research. Okay. So again, you need to really first understand how a sequential SAT will work and how you can parallelize it.
However, what happens is the parallelization doesn't really help so much, because if it doesn't work, then likely it needs a lot more computation and is not going to finish anytime soon. And or if it works, then you have to spend a day or maybe 10 days, and after which will come. If you put 10 machines, it will come in a day. Okay. So parallelization doesn't when you are dealing with problems which are exponential in nature, parallelization doesn't really help, because parallelization only can use linear edge. Okay. So yeah, linear edge here. So if things work in a sequential world, otherwise won't work. Okay. In my experience, either problem get done in a sequential execution, or they don't get done. It rarely happens the problem is just right there. When if you are throwing a 200 machine, 300 machine, it may work. So yeah, that's the experience. Yeah. If anyone no further questions, then we can end this session. Sorry for the initial hiccup.
Hello.
Yeah.
So, okay, I think there is one
This one
more
more question. Yeah.
question.
Should it be? But if anybody else wants to leave, please leave. It's just question answering. Okay, it's your choice. Okay. Should it be in the example shown on screen right now on the current screen? That's what I'm saying. No, no, it's conjunction. Otherwise, it's no, no, no. It's correct. Once again, yeah, it's correct. What others say? I mean, let's have a poll. What others say? I mean, you can do is you can derive. Okay, so this is like a sort of a two clauses given to you. You can apply resolution on these variable, and then you get back the original clause. Okay, so basically this guy implies that guy. Yeah, yeah, it's correct. Otherwise, this you don't get anything out of it. Okay,
Okay,
so
so it seems that now there is no more questions.
yeah,
So let me thank Dr. Ashutosh for such a wonderful preliminary session. Now, at the beginning, I could not do it. Dr. Ashutosh directly ventured into the preliminaries. So, just give you a brief introduction about Dr. Ashutosh Gupta. He is an assistant professor at IIT Bombay. During his PhD, he was affiliated with several institutes like TUM, EPFL, and MPI. And he did his postdoc at IST Austria. And I think briefly he was also affiliated with TIFR Bombay. So again, I would thank Dr. Ashutosh Gupta very much for such a wonderful session. Now, see you all at 1:30 p.m. IST for the main tutorial by Professor Armin Baer. It will start at 1:30 p.m. IST, which is GMT plus 5:30. Okay, so see you all then. Thank you
okay.
very much.
We stop sharing and end.